An inductor is simply a coil or loop of wire which opposes a change in the current within it. Inductance of a coil is measured in Henry. Inductance of a coil will depend on the number of turns in the coil, permeability of the medium inside the coil, cross-section of the core, and the spacing between the turns of the coil. The more number of turns there are in the coil, higher the inductance. Higher permeability of the core also increases inductance. Coils with larger cross-section have higher inductance. In the case of spacing between the turns of the coil, it is the other way around. Smaller the spacing between the turns of the coil, higher the inductance. The inductance in this discussion is actually self-inductance of the coil. A change in the current in the coil induces a voltage within it. 1 Henry is the amount of inductance required for generating 1 volt of induced voltage in the coil when the current is changing at the rate of 1 ampere per second. As in case of capacitance, smaller units are millihenry and microhenry. Just as the change of current in a coil can induce a voltage in it, the change in current with corresponding change in magnetic flux can induce a voltage in a coupled coil which is very near to it or wound over it. That is known as mutual inductance and forms the basis of transformers. This applies only to alternating current which changes continuously. In case of direct current, change occurs only during the moment the circuit is switched on. So practically there is very little opposition to a direct current by an inductor except the minimal resistance of the wire. But when an alternating current is applied to the same coil, there is significant impedance to current flow depending on the frequency of the alternating current, which is higher at higher frequencies than at the usual 50 Hz of the supply voltage. Diagram illustrates a transformer with 2 windings on a core. Usually laminated cores are used for transformers. Here primary winding has NP turns. The primary current is IP. Primary voltage is VP. Secondary winding has NS turns. Secondary current is IS and secondary voltage is Vs. The ratio between the turns of primary winding and secondary winding will determine the change in voltages between the two windings. Here you can see that primary winding has more number of turns than the secondary winding. So this will act as a step down transformer. It will decrease the voltage which is given to the primary winding as a lower voltage in secondary winding. You can see that primary winding is made of thinner wire in this case and secondary winding is made of thicker wire. That is because primary winding with more number of turns will have higher inductance and hence the current in the primary winding will be lesser than the current in the secondary winding in case of a step down transformer. If you want to step up the voltage, it will be connected the other way around. If a lower voltage is given to the secondary winding of this transformer, you will get a higher voltage in the primary winding. But actually, if you connect that way, you cannot call it as primary and secondary. The nomenclature will also have to be reversed. So in a step-up transformer, primary winding will have lower number of turns and secondary winding will have higher number of turns. The ratio of the voltages is having the same value as the ratio of the number of turns. This is a transformer which I can use for the power supply. This is a secondary output. You can see two wires going. That will be 12 volts. And this is the primary connection to the mains supply. The turns ratio will decide the voltage in the output. Suppose this is 230 volt and this is 12 volt output. That's a step down transformer and you need a turns ratio of 230 to 12 to get a step down transformer. The number of turns will be much higher than 230 because you have to cover the current needed and sufficient impedance to the alternating current should be there. So the number of turns will be much higher, and on the higher voltage side, as the current is lower and the voltage is higher, you will use thinner insulated copper wire, and on the secondary side, as the current will be more and voltage will be lower, you use a thicker insulated copper wire. That is the usual pattern in step down transformers. I have just removed part of the cover of the transformer just to show the laminated core. You can see that this core is made of several laminated sheets, and the lamination is needed to prevent eddy currents. The core will have eddy currents, will heat up the core, and that can be prevented by using a laminated core. And when eddy currents are there, that will cause generation of heat and loss of energy, so that the efficiency of the transformer in converting the power will be reduced if you use core without lamination. Core with lamination will improve the efficiency of the transformer. I have used a pair of crocodile clips to connect the secondary winding of the transformer to the multimeter. You can see one connection here. This is one connection and the other connection is here. I have used different colors of wire just for convenience. This is a black wire to one part of the secondary winding. This is a yellow wire, and these will go into the multimeter. One connection is here, another connection is here. So it is displaying a voltage of 10.5 volts. Minimal fluctuation is there. That could be due to fluctuation in the line voltage input. You can see that I have selected at 200 volt range. There are two ranges in this multimeter, 750 and 200. At such a higher range, there could be some error also. Anyway, 10.6 is the approximate output voltage of the transformer at the moment. This will vary depending on the power supply, because AC power supply there could be fluctuation in voltage which could cause a change in the secondary voltage as well. An inductor is also called a choke because it tends to choke the flow of a fluctuating current through it. This property is used in the process of filtering a rectified direct current along with high value capacitors. As the inductance opposes changes in the current, it smooths out the ripples in a rectified DC. But they are not as commonly used as filter capacitors in rectifier circuits, as the inductance needed will make the quite bulky at the low frequency of 50 Hz. At higher frequencies, as the effect is much more, inductors can be used. An important use of an inductor in amateur radio is a common mode choke in feed lines to prevent something known as common mode current, which has been covered in another video on this channel. In the next video, we'll discuss about another passive electronic element, inductor.